Hi everyone, this is lecture number 13 for abstract algebra. Today we're going to be talking about the semi-direct product. I'm going to first give some motivation for the semi-direct product, and then I'll give you a definition and some basic proofs. And then at the end I'll give you some exercises to work on. So to start with an example to motivate the semi-direct product, let's look at a standard example. I want to consider the group D3. Okay, so this is rotations, permutations of the triangle. So if we try to identify D3 as a direct product, we're going to fail. So recall from identifying direct products that we want to find two subgroups, H and K, in D3 that are both normal. But unfortunately, if you try to do this, the natural idea is to try the subgroup generated by R and the subgroup generated by S. But the problem is that R is normal in D3, but S is not. So we can no longer use the direct product. So let me write this out. Notice that R is normal in D3, but S is not normal in D3. I'm going to put the brackets there. And if you want to see why that's true, consider R as R inverse. And you'll see that it just doesn't work. But the problem is that morally you feel like this should be correct. So we know that this is not true, right? We know that it's not isomorphic to R cross S. But it feels right? Because we have all the correct conditions. We have the order of the subgroups multiplied together equals, well, 3 times 2, which is 6. So it equals the order of my whole group. And I also have the fact that these guys have a trivial intersection. Because this is just all powers of S, this is all powers of R, they only agree at 1. You can also argue that 1 is 3 and 1 is 2, so the only common divisor is 1. So it feels morally that we should be able to write D3 as a combination of these guys. And in fact, that's how we usually think about D3. We think of it as like S times R to the K, or just R to the K. So some combinations of S and R's. So the question is, how can we fix this? How can we fix this? And the answer, as you're probably guessing, is semi-direct products. Semi-direct products. So let's see how they work. So really what we want to analyze is, I'm going to call R to be this guy, and I'm going to call the subgroup S to be this guy. And what we want to analyze is the subgroup RS. Okay, so when R and S were both normal, RS had a simple structure. It was just R times S. Very easy. They commuted with each other. It was great. But now that S is not normal, RS is more complicated. So let's analyze the multiplication structure. So let's say I took some things R1 and R2 and R, and S1 and S2 and S. And I wanted to look at what the multiplication of R1 S1 times R2 S2 would be. Because the problem is right now when I look at this, before they commuted with each other. So I could move the R2s over here and I could say it was R1 R2 times S1 S2, which is exactly what we want. Unfortunately, I can't do that anymore in general. And so I want to write this as another element of RS. So as another element of something in R times something in S. So I'm going to do a little trick, which is I'm going to rewrite this as R1 S1 and then I'm going to introduce an extra term, which is after this R2, I'm going to introduce an S1 inverse and an S1, and then S2. So notice that adding this term in doesn't change anything. They just multiply to be 1. But now what I can do is I can notice that this thing right here is actually in R because R is normal. So when I do SR2 S inverse, it's still going to be in R, which means now I've written this as something in RS. It's something which is R1 times S1 R2 S1 inverse. This thing is in R because it's something in R times something in R times S1 S2. And this is clearly an S. Okay, so you should now be thinking that it's kind of funky how this conjugation appeared. So you should be thinking that our multiplication law for RS is completely determined by this conjugation action. By the conjugation of S acting on R. Because we're doing conjugation by elements in S. So if I know everything about this group action by conjugation, I know everything about the structure of RS, and that's exactly what I need to determine the structure of the group. Because recall, when we were doing direct products, all we were really doing was trying to find the structure of this, I think it's called an inner product, RS, and we identified that as a direct product, which is much easier to think about. The problem is now we can't do that, so we're still going to look at the structure and just identify it as something called a semi-direct product. Okay, so this action, S acting on R, induces a map, so it induces a map which I'm going to call phi from S to the automorphisms of R. And I'm just going to denote phi of S equals phi sub S for notational clarity. So this map, of course, just sends an element S to like the conjugation action. It's like an automorphism which is conjugating by this element of S on any element of R. Okay. So finally I can make a definition. So I'm going to define the semi-direct product, which I'm going to notate like this. So this is kind of like an X with an extra line attached. And note that the X opens up to the normal subgroup. It opens up to R, which is normal. And it's closed on the not normal subgroup. So this is the group where my set is R cross S. And I have this multiplication law, which is defined by R1 comma S1 dotted with R2 comma S2 should be, as we described above, R1 of phi sub S1 of R2, and then comma S1, S2. So this looks a little weird at first. And the reason why I like to motivate it this way is because it looks really weird if you just learn the definition like this and don't see where it's coming from. But recall, all the way up here, is that really this funky term is coming from this. It's saying I have to conjugate by S1. Conjugate R2 by S1. And that's all that this term is saying, is conjugate R2 by S1. So I have this funky term, and then everything else is kind of normal, how you would expect it to be. So hopefully you should be able to convince yourself. So convince yourself that D3 is isomorphic to RS, which is isomorphic to our semi-direct product S. And note that I write the phi down here because the phi is actually important in the structure of the semi-direct product. Sometimes it's not written, and that's either when it's usually just when the phi is not ambiguous, so it's already been defined, and that's what you're going to be using. So, but usually it's written, and that's the thing you should use. Okay, so this is for a particular example for D3. So now you should know the general structure. So let's generalize it. And I'll give you a more general definition. Okay. So let's suppose G is a group with subgroups H and K. With subgroups H and K, G, and we have that H is normal in G. So this is a setup we had before. Now let var phi be a map from K into the automorphisms of H. And if you ever forget which way this map should go, if it's like H into automorphism of K, recall that H is the normal one. So you can act on it by conjugation because it stays within H. Conjugating things stays within H. So it has to be K acting on H. It can't be H acting on K because K might not necessarily be normal. So it doesn't even make sense. So it has to always be K into the automorphisms of H if H is the normal one. So phi induced by conjugation action of K acting on H, then the semi-direct product of, oh, whoops, wrong way. So it opens up to H. So the semi-direct product is the group H cross K, comma, my multiplication, where H1, K1 dotted with H2, K2 equals, as you should suspect, H1 var phi of K1, comma, H2, comma, K1, K2. Okay. So I just said it was a group. I didn't prove it for you. So I'm going to give you outlines of a proof and I want you to fill it in yourself because I think it's a good exercise. So proof, this is a group. That's what we want to prove. Okay, so you need to prove three things: identity, inverses, and associativity. I will do the identity and I'll kind of give an outline for inverses and I'll leave associativity up to you because that's not very interesting. So, okay, you should hopefully guess that the identity should be 1 comma 1. So let's just test that it works. So this is going to equal, well, okay, it's going to be 1 times var phi of var phi sub 1 of h, comma 1 times k. Okay, but var phi sub 1 is just a trivial action. Doing 1 h1 inverse is just h. So I'm going to just get h comma k. Okay, so it's the identity there, and you can check it the other way as well. Not too bad. Okay, inverses. So here, the inverses is not exactly what your first guess might be. You can probably reasonably guess that given the new multiplication, you should be a little tricky with what the inverse actually is. So I'm going to write it out and you should verify it yourself. If I have something hk, its inverse is going to be k inverse h inverse k comma k inverse, and show that this equals 1 comma 1. Okay. And then finally, I'll leave associativity as an exercise. And so this guy is in fact a group, even though I didn't prove most of it. So now let's do a theorem to actually show that the inner product is the semi-direct product. Because that's really what we want to show at the end of the day. Once we get that, we're good. So if H is normal in G and H intersect K is trivial, then HK is going to be isomorphic to H semi-direct product K. Okay, let's prove this. Okay, so we're just going to prove it by, well, defining an isomorphism. So define some map var phi, which is going to take a pair H comma K. So that's in the semi-direct product. And it's going to send to something in here. Hopefully your guess should be HK. Pretty standard. So this map is well defined, and it's a homomorphism basically from construction of the semi-direct product. If you want to verify this, please try it out. But kind of from the way we constructed the product and the semi-direct product makes this a homomorphism from construction. Okay. So now we need to show that it's bijective. So homomorphism is injective if its kernel is trivial. So kernel of var phi is going to be those guys h comma k such that hk equals 1. Well, this implies that if let's say there's some kind of hk in here, then hk equals 1. So h equals k inverse by multiplying on the right by k inverse. But this means that h is in k, right? If it's k inverse, then it has to be in k. But h was also in h, so this implies that h is in h intersect k. It's in both of them. But from assumption, h intersect k was just 1. So this implies that h equals 1, which also equals k. Which means that the kernel is trivial. Since we showed if something is in there, it has to be 1 comma 1. Okay. Now, for surjectivity, just let hk be in the inner product, this, and it should be pretty clear to you that var phi of h comma k equals hk, so it's surjective. And thus the function is a homomorphism and it's bijective, so it is an isomorphism. And we've proven an isomorphism between the semi-direct product and the inner product. And finally, I should note, as we did with the direct products, is if the sizes of my two subgroups now multiply together to be sides of the whole group, then the whole group is the semidirect product. Then G is isomorphic to H semidirect product with K. Okay. Now let's do a quick corollary, which is looking at this map var phi, K into the automorphisms of H. So the question is what happens when this map is trivial? So when it has some interesting structure, then the semidirect product becomes interesting. But what happens when var phi is trivial? If var phi is trivial, then hopefully you should guess that all the interesting structure that comes with the semidirect product vanishes and we just get the direct product. And that happens to be correct, is isomorphic to H cross K. So our proof, very quick, is just looking at the multiplication law. So when it's trivial, this becomes H1 var phi K1 of H2, comma K1 K2. But since var phi is trivial, this just maps to H2, so we get H1 H2, comma K1 K2, which is exactly what we would get during the direct product. So it's the exact same as H cross K. And so hopefully this should give you the intuition that the semi-direct product is generalizing the direct product. It's a more powerful generalization, which works in scenarios, as I'm about to show again, with some examples, with dm, which is in general going to be isomorphic to R semi-direct product with S, where my map var phi sub S of some general thing R to the K is going to equal S R to the K S inverse, which is going to equal R to the negative K. And this fully defines my semi-direct product on this group. Okay, now let's do one other example, which is a little more enlightening. So let P and Q be primes with P less than Q. Hopefully this should be reminding you of some Silo theorem stuff, which is what we're going to use. And let the order of my group be P times Q. So for example, 6 or 15 or 77. And what I want to prove is then G is a semi-direct product of Z mod Q and Z mod P. Z mod Q, semi-direct product with Z mod P. Okay. So, Silo's theorem tells us there exists two there exists a P and a Q Silo subgroup. Let's call them HP and HQ. Okay. Now, you should notice that N sub Q has to equal 1 or P. This is just from third Silo theorem. And you should also remember that N sub Q is 1 mod Q. So this could mean it's 1, Q plus 1, 2Q plus 1, 3Q plus 1, so on and so forth. But the problem is that Q is greater than P. So if NQ was, say, Q plus 1, then it couldn't be P, because P is strictly less than Q. Which means that NQ, combine these two facts, NQ has to be 1. Which means that HQ is normal in G. Okay, great. So this is exactly the setup for semi-direct products. The only thing we need is that the orders have to multiply to the order of the whole group. And luckily, we know that order of G is P times Q, which is exactly the order of HP times the order of HQ. Okay, great. Thus, I get that H is isomorphic to HQ semi-direct product, HP. And now we're going to do a little more analysis of what this var phi is. So recall that HQ is Z mod Q and HP is Z mod P in this case, so I get the theorem I stated before. So var phi is going from Z mod P or HP to the automorphisms of Z mod Q. Now, this is a fact. I don't think I've proven this to you, but you should try to convince yourself of it or try to prove it yourself, which is that the automorphisms of Z mod Q when Q is a prime is isomorphic to Z mod Q minus 1. Okay. Which means that var phi is now a map from Z mod P to Z mod Q minus 1. Now, I can try to analyze all the different kinds of maps that can occur here. And the thing I notice is that var phi is completely determined by where it sends 1. Since Z mod P is cyclic, if I know where it sends 1, then I know where it sends var phi of 1 plus 1, or 1 plus 1 plus 1, so on and so forth. So var phi determined by the value of var phi of 1. Okay? Now notice if var phi 1 is 0, then the map is trivial. Var phi of 1 equals 0 implies var phi trivial, which by our corollary above, this implies that G is isomorphic to Z mod Q cross Z mod P. And in particular, you should notice, I'm not going to prove this to you, but convince yourself of this or prove it yourself, that if P does not divide Q minus 1, then var phi of 1 has to be 0. So an example is, let me think, um, T equals 3 and Q equals 11. Then 3 does not divide 2. And then you get that if G is of order 33, it has to be Z mod 3 cross Z mod 11. Otherwise, if P does divide Q minus 1, you might have more options. So basically, we've partially described using semi-direct products what groups of order PQ are. I mean, we've fully described them as semi-direct products, but there are a couple of options when you have the fact that P divides Q minus 1. Okay, great. So now that you've gotten a decent introduction to semi-direct products, I'm going to give you some exercises that you can work on your own for practice. So the first one is let rho from G to G be a homomorphism. It's a homomorphism such that uh, I'm going to get kernel of rho equals kernel of rho squared or rho composed with rho. Okay? Then I want you to prove that G is isomorphic to kernel of rho, semi-direct product with the image of rho. Okay. Second exercise is I want you to write or describe Sn as a semi-direct product. Semi-direct product. Okay, so think about the structure of Sn and any subgroups you can use, one of which is normal, to describe it as a semi-direct product. And then finally, I want you to classify or find all groups of order 21. Okay, so you could try to use our previous discussion right above these exercises. 21 is 3 times 7. So it has the form p times q, but notice that 3 divides 6. So you're going to get some ambiguity in that semi-direct product. So try to figure out all the different kinds of groups there are of order 21. Okay, thank you guys for listening. I hope this was helpful.